Welcome to the Explainer. We are jumping right into things today, dropping you straight into the retro-futuristic cinematic world of Commodore 64 assembly programming. We're going back to an era where developers didn't have the luxury of endless gigabytes of RAM or massive modern game engines. Instead they had raw silicon, a blinking cursor, and absolute unfiltered power. So let's deconstruct how a game is actually built at the absolute lowest possible level. There's this incredibly powerful quote from our source material that really sets the stage perfectly. In assembly, you don't write a game, you build a nervous system that communicates directly with the hardware. Just think about that for a second. Because when you're programming in assembly language on an 8-bit machine, you aren't just writing lines of code that some other software is eventually going to interpret. You are literally wiring a digital machine. Every single command you type, it acts like an electrical impulse sent directly to the physical chips right there on the motherboard. You essentially become the ghost in the machine. To really grasp this, we've got to look at the physical hardware itself. When we deconstruct a classic C64 game, the whole journey kicks off at the hexadecimal memory address 1000. And by starting our machine code right here, we're doing something that modern developers almost never do anymore. We are bypassing the operating system entirely. We aren't politely asking the OS for permission to draw a pixel or play a sound. No way. We're grabbing the keys to the kingdom and driving the hardware ourselves.
Which brings us to a really crucial concept, bare metal architecture. In a nutshell, it's writing pure machine code to directly manipulate physical hardware chips and memory registers. There's no software middleman here, guys. There is absolutely no safety net. If you accidentally drop the wrong hexadecimal value into the wrong memory address, boom, the entire system instantly crashes. But if you get it right, the level of control and the sheer efficiency you unlock is just absolutely staggering.
So let's actually see this anatomical deconstruction in action. We'll look at a game called Formula. Taking a top-down view, we've got our actors. You have one player controlling a Formula race car sprite and two enemy square sprites just darting across the screen. The objective is elegantly simple. The player just has to complete 9 successful vertical screen transitions, moving from top to bottom, all while dodging those enemies. Sounds simple enough, right? But under the hood, the sheer amount of manual hardware management required to pull this off is fascinating. To make this game actually run, the developer has to construct an infinite lightning-fast game loop. Here's how it breaks down. Step 1, read the physical keyboard matrix directly, specifically at memory location 197, to see if the A, D, W, or S keys are being pressed. Step 2, mathematically update the sprite's position on the screen. Step 3, check memory address D01E to see if the hardware's native collision detection got triggered. And Step 4, pulse the SID chip to create that classic engine sound. This exact loop repeats thousands of times a second, just constantly commanding the hardware. We really need to contrast these two totally different paradigms. On one hand, you have sluggish software interpretation. This is exactly what happens when you use a higher-level language like BASIC. Every single command you write has to be read, then translated by the OS, and then eventually sent to the hardware. Honestly, it's like trying to drive a car with the parking brake fully engaged. But then, on the other hand, you have the assembly approach, direct hardware manipulation. Here, you are injecting instructions straight into the VIC-2 graphics chip and the SID audio chip. It's blisteringly fast, but to do it, you need a really intimate knowledge of the machine's anatomy.
And building this digital nervous system means you need to know some literal hardware hacks. For instance, to move the player's car, you directly overwrite the values at memory addresses D000 and D001. But here's where it gets wild. Because the C64 screen is wider than 255 pixels, which happens to be the maximum size of an 8-bit number, the programmer actually has to manually track a 9th bit in a completely different register just to scroll smoothly across the right side of the screen. Plus, you have to explicitly read that D01E collision register at the very start of your loop just to clear a known native hardware bug before you can even check for a real crush. And finally, to get those engine noises, you aren't playing an audio file. No, you are mathematically manipulating the sawtooth waveforms in the D400 audio registers to literally mimic the sound of a motor.
So this really sets the stage for the ultimate showdown, assembly versus BASIC. Which paradigm truly ruled the 8-bit era? You might be wondering, why fight with complicated 9th-bit mathematics when the Commodore 64 had a perfectly user-friendly BASIC language built right into it? Well, let's look at the showdown. In the left corner, we've got a game called Trike. It's a simple racing game written entirely in that standard user-friendly BASIC language. And in the right corner, Formula, the game we've been deconstructing written completely in bare metal assembly. Now, both of these games feature a sprite moving across the screen. They both check for boundaries, and they both handle collisions. But the performance difference between the two? It is nothing short of mind-bending. The absolutely crucial point here is this staggering number, 1,705. The assembly game isn't just, a little bit faster. It executes its screen traversal a massive 1,705 times faster than the basic version. Let that sink in. This isn't just some minor optimization, it's a completely different paradigm of computing altogether. This specific speed multiplier perfectly represents the technological revolution that defined an entire era of commercial video gaming. Just look at the memory footprint. In an era where literally every single byte was precious, the basic program takes up 1,934 bytes. The assembly program, despite actually doing more, is nearly 50% lighter at just 1,006 bytes. But the real shock here is the speed. It takes the basic game 14.5 agonizing seconds to traverse the screen. The assembly game, it does it in 0.0085 seconds. Actually, the assembly game is so incredibly fast that the programmer literally had to write empty delay loops into the code just to slow the processor down. Otherwise, the human eye wouldn't even be able to see the car moving. How crazy is that? This elegantly summarizes the true legacy of assembly language on 8-bit machines. It offered extreme memory efficiency and blistering execution speed. It gave developers absolute, uncompromising control over the physical hardware physics of the machine. This bare metal approach wasn't just some fun academic exercise. It was the absolutely essential, only viable path for true commercial gaming. Every single legendary title that made the C64 a household name, they were all built utilizing these exact same bare metal techniques. Which brings us to a final thought for you to ponder. Today, we build software using massive engines, endless layers of abstraction, and operating systems that hide the physical hardware from us completely. We trade that raw control for convenience. But looking back at the sheer, unadulterated power unlocked by directly manipulating those silicon chips, well, one has to wonder. In an era of endless software abstraction, what true power have modern developers lost by moving so far away from the bare metal? Thanks for joining me for this explainer. Keep questioning the code.